Hello chemists, this is Ms. Placino and you are watching a tutorial on error analysis. Error analysis is a very important aspect of the lab class. In nearly every lab you do, at the conclusion of that lab, you're going to have to assess the quality of your results. And we do that in one of two ways depending upon the lab. The first you're probably already familiar with, percent error. Just to remind you, percent error is calculated by taking your experimental value or your calculated or measured value, subtracting the actual value, dividing by the actual value, and then multiplying by 100. Please take note, there are no absolute value bars in this equation. Percent error can be negative. We'll talk about it a little bit later this video, but the sign of percent error proves to be really important while trying to figure out what happened or what went wrong during your experiments. The other means that we can use to evaluate data is percent range. You might not be familiar with this one. Anytime that you're doing really anything in the lab, you tend to do it multiple times. So to calculate the percent range, you're going to take the highest value minus the lowest value that you've either measured or calculated, and then divide by the average of those values and multiply by 100. Due to the nature of this calculation, percent range is always going to be positive. For this video, I want to focus on percent error. We'll use percent range, or we'll cover percent range in more detail as we get into those specific labs. All right, error analysis is really all about answering the question, why is the percent error not equal to 0? Regardless of how carefully and methodically you work, there's a good chance that you are not going to get it perfectly right every single time. So in order to talk about error analysis, I'm going to use one of my favorite TV characters of all time, Homer Simpson. And Homer's got a bunch of different ideas about what could cause errors, and we're going to talk about why these are probably not the best errors to cite. So during this video, we're going to talk about mistakes in carelessness, instrumental limitations, external influences. Then we'll finally get into some valid sources of error, which hopefully leads you to conclude that 1, 2, and 3 are not valid sources of error. And finally, the impact of the error on your data. All right, mistakes in carelessness. So I go through and I read your labs, and in almost every lab, you're asked to state your percent error or your percent range, and then talk about what could have happened to make it not equal to 0. And I'll get things like measuring incorrectly. So you can't use a graduated cylinder right. Preparing a solution incorrectly. You were asked to make 0.5, you made 0.05. You spilled something, or your lab partner spilled something, or you simply did not follow the procedure. All these are kind of moments. These are things that you can totally correct and take care of if you are just a little bit more careful. So these, as the title suggests of the slides, are just mistakes and general carelessness. These are not valid sources of error. Please do not cite them in your lab report. You are not going to earn any credit for that. Instrumental limitations. Okay, if you're not going to blame yourself, maybe we're going to blame the instruments. For example, maybe the scale was not calibrated correctly. Maybe the markings on the burette are wrong. Or maybe the tick marks do not give precise enough measurements. I've seen all of these as reasons for why percent error is not equal to 0. You got to make do with the tools that you've got and use them the way they are intended. For example, if the scale is not calibrated correctly, you put a beaker on it and it tells you it weighs 2 grams, don't use that scale or bring it to the front and get it calibrated. It is highly unlikely that the markings on the burette are wrong. And finally, that last one, the tick marks do not give precise enough measurements. That's not going to affect your percent error at all. That would maybe affect the number of significant figures you have in your percent error. These are invalid sources of error as well. We're going to make the assumption that the instruments that we're working with are calibrated correctly, are working correctly, and if you've got some reason to think that that is not the case, bring it to me, we'll take a look at it, we'll get you a new one or get it fixed or calibrated. External influences, my favorite group of invalid error sources. The conditions changed. So for example, the first day when you were doing your lab, the temperature was 75 degrees in the classroom, and by the end of the week it was suddenly 78 degrees in the classroom, and that must have screwed up everything. The solvent evaporated. From time to time, you're going to have to store solvents in the back of the classroom. They're usually in a squeeze bottle. Some of the bottles have caps, some of them don't. So students like to tell me that some of the solvent could have evaporated and that changed everything. Please keep in mind that the school does not get up to like 100 degrees Celsius overnight. Dust particles have settled. So the lab room itself is not pristine clean, but it is very unlikely that massive amounts of dust, enough to skew your results, have settled on your product. A draft over the scale, the precision balances are extremely sensitive, and after you actually just kind of move your hand over the top of it without touching it, just moving the air around is enough to cause the last decimal place, to fluctuate. You're talking about, in most cases, thousandths of a gram. Probably not going to have a substantial influence or impact on your error. And my personal favorite, contamination. The beaker was contaminated, and that's why my results are terrible. All of these sound like you're just blaming some external force, something that you have absolutely no control of, and in most cases, you're really reaching here. These are invalid sources of error. Please do not cite them in your lab report. You are not going to receive any credit for that. So just to recap, our invalid error sources tend to be vague. For example, contamination, that could apply to nearly any lab out there, and that's why you wash your glassware, so that you don't have contamination issues. A lot of times it's the result of carelessness. You just don't measure things correctly, or you spill things and try to use the solution anyway. And sometimes it sounds like you're just blaming outside factors. You're just kind of grasping at straws, trying to think up any reason why percent error is not equal to 0. Valid sources of error are really the opposite of that. They're very specific to the lab. They're often correctable with better technique. This is, for a lot of you, the first time that you've taken chemistry since you were a sophomore. So you're not expected to be perfect. If you're following the procedure the best you can, you should be okay, but your technique is going to not be perfect at the beginning of the semester. And finally, valid sources of error sound like you're taking ownership for imperfect data instead of blaming outside influences. So I want to practice a little bit with this, as this is something that's often difficult for students to really grasp. So for the next 12 questions, you are given a cited error. Your job is to determine, is it valid, yes or no, and provide a few word explanation supporting your choice of whether it's valid or not. Pause the video, give these a try. All right, so number 1, the scale was not calibrated correctly. We just talked about this. This is not a valid error because you're blaming the instrument. Again, if you have reason to think that your scale is not calibrated correctly, you should calibrate it. That's really easy. We'll show you how. Number 2, the sample was heated too aggressively and splattered. This is a valid source of error because it's correctable with better technique. It's also very specific to a lab. If you didn't heat something in the lab, you cannot use this as a source of error. Number 3, the analyte solution was over-titrated. This happens all the time in Regents chemistry. This is a valid source of error. Again, it's correctable with better technique. This is also why we tend to do titrations in triplicate. Number 4, the beaker was contaminated. No, it's just way too general. That could apply to anything, and again, this is why you wash your glassware. Number 5, the volume of the liquid inside the graduated cylinder was misread. Again, not a valid error. This is carelessness. By now, you should be able to use a graduated cylinder correctly. Number 6, the thermometer was broken. Why on earth would you use a broken thermometer? No, this is not valid. You are blaming the instrument, and although it may be broken, you're kind of crazy for using it in your experiment. And if you've got broken glassware, equipment, or something you think is just not working properly, bring it to me so that we can check it out. Number 7, due to improper digestion, the precipitate passed through the filter. This is not the digestion you learned about in biology class. This is a technique that we'll use in lab. This is a valid source of error. The filter paper is not perfect, and some of it will pass through. But if you digest it better, and again, technique we'll learn in lab, you should be able to minimize this error. Number 8, difficulty gauging when the crystals are completely melted. We'll do melting point analysis a couple times this semester. This is valid. Correctable with better technique, and also once you get more experience. Number 9, the solution was made incorrectly. Not valid. It's careless, it's also too vague. Number 10, too much solvent was added to the volumetric flask. This is not a valid source of error. You need to be able to make solutions correctly. It's careless. If you do add too much solvent to the volumetric flask, you can't just try to pour it off and start again. You'll lose some of your solute that way as well. So unfortunately, you have to dump the whole thing and start from the beginning. Number 11, the crystals were not heated long enough and water remained. This is valid, correctable with better technique. And last, some of the solute may have come out of solution. This actually depends on really the situation as to whether this is valid or not. So for example, the majority of the solutions that we make in lab are going to be at a relatively low concentration and a relatively soluble solute. So it is unlikely that it is going to be a problem. However, if you're working with something that is relatively insoluble, or you're working with solutions of high concentration, it is possible that solute could come out of the solution. More often than not, I would say that this is an invalid source of error. All right, so you've got your valid source of error. Good for you. Remember, it needs to be a realistic possibility. You can usually correct it with better technique. You probably noticed that. The last set of practice problems, the ones that are valid, can be fixed by you just doing a better job. And you can usually support it by empirical evidence. So what we mean by empirical evidence is that you can look and see that something went wrong. For example, everybody's running the reaction and ending up with a white precipitate. Yours is orange for some reason. That's probably a source of error, and actually probably something that would warrant restarting the experiments. All right, so you've got your valid error. This is a question that causes a lot of frustration for students. Will the error that you cited cause the results to be too high or too low? This requires a lot of thinking. If your error causes the results to be too high, you think back to the percent error formula, that means that your measured or experimental results are greater than the actual value. You're going to end up with a positive percent error. If your error causes results to be too low, your calculated value is going to be less than the accepted value, and you're going to end up with a negative percent error. This is why it's really important to not use absolute value bars and to make sure that you're always doing experimental minus actual when you're calculating percent error. We've got this flowchart to kind of help you out with your decision-making process. So first thing you need to do is calculate percent error, and really that's the easiest part of the whole error analysis process. Percent error, unlikely to be equal to 0. So do you have any evidence of errors? Did you end up with a fluorescent pink solution when you were doing a titration? Did you see splatter marks on the table? That's evidence of errors. If so, what happened? If not, what could have gone undetected? So what could have happened that made everything look like everything was going okay, but in reality there was a problem? Figure out what impact that error would have on measured data. Usually you're looking at things like mass and volume as measurements in this class. Look at the calculations that you perform with those measured values and see what's going to happen with your calculated values. Ultimately, does the error you cite agree with the sign of percent error that you calculated? If it does, awesome, you're done. If not, you get to go back more or less to the beginning and repeat with a new error. That's what makes error analysis so challenging, is that it's not just enough to have found an error that is a viable possibility. It has to explain what's happened with your data, and that is very, very challenging to do. So let's do a little bit of practice with this together. So you're given the piece of information that you were trying to find or determine. In this case, you're trying to find the mass of the precipitate produced. And our valid source of error is that some of the precipitate has passed through the filter paper. So just to give you a visual, here's your gravity filtration setup. You've got your solution that you're going to pour through a filter with filter paper. Ideally, the solid should get stuck on the filter paper, or solid or precipitate. But in this case, you've noticed that some of your precipitate has passed through and has ended up in the filtrate. This is not ideal, but it's going to happen from time to time. Filter paper is not perfect. So if you think about it, you're trying to find the mass of the precipitate produced, and some of the precipitate is now down here in the filtrate. It's safe to assume that the mass of the solid that you collected is going to be lower than it's supposed to be. You collected less precipitate than expected. So if you were supposed to end up with 5 grams and you've only managed to recover 4.5, hopefully you recognize that percent error is going to be negative. Let's do another one together. So you are trying to find the melting point of a solid. Your valid source of error is that it is difficult to gauge when the crystals have melted. One technique that we'll use for melting point determination is hot water bath. So under here we'll have something like a hot plate. You'll heat up that beaker of water, and as that heats up, it's going to cause your sample, in this case stearic acid, to melt. So if the error is it's difficult to gauge when the crystals have melted, what's really going to end up happening is that you have an inaccurate melting point. This could go one of two ways. Your melting point could be too high, or it could be too low. If it's too high, that means that you heated past the melting point, so you couldn't tell that the whole sample was melted. If it is too low, that means that you took the final temperature too soon and not all of the crystals have melted yet. So your percent error could be positive or negative depending upon which of these issues occurred. All right, with the next two, why don't you pause the video and try them out for yourself. All right, you're trying to determine the percent mass of water present in hydrate. Your error is that the sample was heated too aggressively and splattered. So we've got a crucible being heated over a Bunsen burner flame, and we say the sample splattered. As you heat it, really only the water molecules are supposed to be driven off as steam, but you were aggressive. You're rushing, and you ended up with a bunch of your actual compound coming out as well. When you go to calculate the percent mass of water present in a compound, you look at the mass of water that has been driven off or has evaporated or has turned into steam, divided by the mass of the hydrate compound that was used. So the mass of the hydrate compound is going to be the same throughout. If you've splattered, what's going to happen to the mass of the water, or it seems like the mass of water that was driven off? Hopefully you're thinking that that goes up. That's a sad looking arrow. I think I'm making it worse. Anyway, the mass of the water is going to appear to be higher than it is in reality because in addition to losing water molecules, you have also lost some of your compound. And as a result, the percent error is going to be positive. Your calculated percent mass of water is greater than the actual percent mass of water. So again, positive percent error. Last one. So you're trying to figure out the molarity of a sodium hydroxide solution, and your error is that the analyte solution was over-titrated. So this is what a good titration looks like. You got that pale pink endpoint with phenolphthalein. When you say over-titrated, this is what you've got. It happens. This is why we do titration in triplicate. So we're going to, again, I don't love this formula, but we'll use it for this example. MAVA equals MBVB. We're talking about we're trying to find the molarity of the base, and the analyte solution was over-titrated, which means we used more or less sodium hydroxide than we were supposed to. Hopefully the word over is a giveaway. We used more NaOH than we needed to. These are going to remain constant, the molarity of the acid and the volume of the acid. The volume of the base is going to be higher than it's supposed to be. So what's going to happen to the molarity of the base that we calculate? That's going to end up being lower than it is in reality. Therefore, percent error is going to be negative. This is a little bit more complicated error to analyze, as you have to jump through some hoops. You've got to think about, okay, over-titrated, I used too much. What impact is that going to have? It's going to make the base seem like it is less concentrated than it actually is. Negative percent error. Let's wrap up with some conclusions. The accuracy of your data is going to be assessed using percent error. Remember, percent error formula does not have absolute value bars present in it. It can be positive or negative. Once you calculated percent errors, you need to cite a valid source of error. Remember, valid errors are specific to the lab, relate to correctable technique problems, and do not blame external or uncontrollable factors. Don't blame things like contamination, equipment, and clumsy lab partners. Those are never going to be valid sources of error. Finally, the cited error must agree with the sign of your percent error. Again, that's why it's really important to make sure that you are using the formula correctly. This is something that is difficult to do. It requires a lot of thinking and sometimes going through and looking at the impact an error is going to have on your calculation. Don't get discouraged or frustrated with it. This is something that everybody struggles with, and you are going to get better as the semester progresses.